Hello everybody and welcome to the NPTEL online certification course on microelectronics devices to circuits. We start today's module. The name of today's module is multi-stage amplifier with spice simulation. So, what we will do in this module of approximately half an hour is give you an idea about the structure of a multi-stage amplifier, and then we will look into how to design a spice deck file in order to solve a multi-stage amplifier, and what parameters need to be extracted from this amplifier design. Now, so let me just recapitulate what we need to do. So, we will first start with CMOS operational amplifier in the outline of the talk, as you can see, and then we will do the spice coding of the CMOS op amp, and then we look into the open loop gain and the closed loop gain for operational amplifier, and then we will also show you a spice code for a unity gain amplifier or a unity gain configuration of operational amplifier. Before we go forward, therefore, let me recapitulate what we did in our previous turn. In our previous turn, we actually looked into what are known as differential amplifiers, right? Differential amplifiers, both BJT based design as well as CMOS based design. We also saw that you need to give a common mode signal to both of them initially, so that they are in the active region, and we do not want them to go into cutoff region, saturation region drastically, and therefore, from active to cutoff and cutoff to active should be the switching parameter which will be available for BJT as well as for CMOS. We also saw that common mode signals are, and that is one of the major prime importance of concern, is that all your common mode signals, right, which is basically noise, for example, common mode signals to both the arms of your BJT, they get rejected. So, all your common mode signals have got very low gain, very low gain, right, and as a result it gets rejected very easily, which means that if you feed a noise to both the arms of a symmetrically coupled, symmetrically designed differential amplifier, the noise will be easily rejected. Whereas, the difference signal which we had defined as ID or IDV as the difference signal between the two arms of the amplifier, they gets amplified drastically, and the ratio which we had already defined earlier, a common mode difference divided by differential mode gain divided by common mode gain here was referred to as CMRR, and this should be as high as possible. Ideally, this should be, ideal value is, as I discussed with you, should be equals to infinity. So, if you design an operational amplifier or a differential amplifier is no doubt the first stage of the operational amplifier. So, today I will show you the second stage of the differential amplifier and show you how it works out properly as a single stage amplifier, op amp. So, we will do an operational we will do show you the circuit diagram of an operational amplifier when we cascade sort of a differential ended operation with a single stage amplifier, right. We also saw, and we also came to the conclusion that whenever you are designing an amplifier, it is always advisable to first of all design an amplifier with, let us say, high gain, right, and then cascade it with high swing, right, and that is what is basically an op amp, right, op amp. So, this will be a differential amplifier, diff amp. So, the first stage of any operational amplifier is basically your differential amplifier, and the second stage is basically a high swing stage or a high gain stage, and that results in a basic understanding of the operational amplifier. So, this is the basic flow which we have been doing it for quite a long time, and let me therefore come to and show it to you the basic diagram of a CMOS operational amplifier. This is a typical diagram of the operational amplifier, out of which if you see very carefully, I will just divide the whole thing into few parts. So, it is easier for you to gather information for each one of them, and I am doing it like this. So, this is part number 1, right, and then we have part number 2 here, this is part number 3, and this is part number 2, right. So, you have part 1 here, right, P1, and then you have P2 and you have got P3 here in all respects. You do have your design here. I will first concentrate on P2 and then we will go to P3 and P4 as we move along. If you look at P2, right, the part 2 which you see here, it is nothing but a differential amplifier with M1 and M2 as the input devices, and M3 and M4 are basically the cascoded device or the load device. I will just show you, and if you look at M5 is nothing but the current source which is available to you. Now, let me draw for you this diagram only in a schematic mode and you will see how it works out. As you can see, therefore it will be something like this. This is again a PMOS and we are assuming a PMOS load, and this PMOS load is this is mirrored here. So, this is current mirrored, and then we have got here one NMOS driver, another NMOS device here, and then we have got this coming out like this, this and this. So, this is M1, M2, M3, M4 and M5, right. This is the, so this M5 is primarily the ISS, which means that this is basically the tail current source, right, and this is responsible for giving the current to both this arm as well as this arm, right. And you have to make this M5 is analogous to your ISS or the current source, and therefore, you will see its aspect ratio is very large, you see 4.5 by 1 micron. So, this is basically this design is based on a 1 micron technology, which means the channel length of all the transistors used here is approximately 1 micron, and the ratio, if you look at W by L ratios of M5 is typically very high, right. It is 4.5 micrometer by 1 micrometer, right, and your VSS is latched to minus 2.5 volts. So, it is not grounded here, if you go back it is not grounded here, but this is VDD which is plus 2.5, and we have got minus VSS which is basically minus 2.5, and therefore, the total swing, the total available the total voltage available, swing available to me is basically equals to 5 volts, right, and this is L equals to 1 micron technology which people have been using in this case. As I will give you the operation and then we can go step by step, one step ahead. See, if you remember that the gain was given as equals to GM times RD, right, where GM was the transconductance of this M1 and M3. Assuming M1 and M3 are equivalent in nature, and also assuming that they have been properly biased in the active region, I can safely write down the overall gain to be equals to GM times RD, where GM is the transconductance of this device as well as in this device, and RD is basically the resistance offered by M3 and M4 load devices, right. So, that is the reason you typically like to have these as PMOS devices, because PMOS has got a hole as the charge carriers, and therefore, its mobility is low, and therefore, its current is small, which results in a higher resistance. Higher resistance means obviously a higher gain in the output side. So, the output has been taken from this place. If you see very carefully, the output is taken is single ended output, right. So, this is the output which you see. So, if you look very carefully, this is the output here, V out. So, this is also known as a single output operation. Why single output? Because you are only taking output from a single end and you are not taking from the double end, right. So, your gains will be approximately half. Let us see how it works out. Let us suppose your V in 1 is given here, and this is say M1, M2, and this is V in 2, and let us suppose V in 1 is much larger as compared to V in 2, and therefore, V in 2 is cut off, right, at this stage, and all the current through this flows through this arm and it goes to M3, right. So, what I am trying to say is that V in 1 is typically very large, much larger than the threshold voltage of M1. Therefore, what it does is it carries all the current from I5, M5 into through M1 onto M3. Now, in M3 your gate and drain are shorted. So, your VGD is equals to 0, gate to drain is always equals to 0, which means that VGS gate to source, this to this, right, is this one, and gate to drain are both equal to each other. So, VGS equals to VGD, right, VGS equals to VGS gate to source is equals to gate to drain, right. because gate to drain is actually equals to 0, gate to drain is equals to 0. Just a minute, I will just make some small corrections here. See, here is that your source and your drain voltage and your gate voltage are equal. So, Vg and Vd are equal. So, if you put source here Vds, right, and you put Vgs, so they are always equal. So, your drain to source voltage is always equals to gate to source voltage, implying that the device is always into saturation region of operation, because if you remember, the region of operation was Vds should be greater than equals to Vgs minus Vth, right. That was what was told to you, it should be less than equal to. For PMOS it should be less than equal to, but since it is always equal to, therefore, this will always be in saturated state. So, they will always behave like a resistor if you short this thing where gate to drain, we short gate to drain. Further, you also ensure that this potential M4 gate potential is exactly equal to the drain potential of M3, right, and therefore, this is sort of a replica here. So, all the current which is flowing from here, exactly the same current will be flowing through this arm, right. This is known as a mirroring action in analog design. This is known as mirroring action. As a result, if you remember, for the current to be same in two arms of two identical MOSFETs, gate to source voltage should be equal. First of all, threshold voltage should also be equal, and you also have to ensure that if it is in the triode region of operation, the drain to source voltage should also be equal, right. So, all these three are ensured to be equal for both M3 and M4 if you simply short gate and source of M3, right. And as a result, the same current which is flowing from this arm, exactly the same current flows through this arm and goes through V out, because this is cut off. So, the same current flows through V out, right, and therefore, whatever current was flowing through this is ISS is coming out here, this multiplied by RD is V out. So, therefore, you get V out to be equals to ISS times RD in a general sense, and as a result, that is the voltage drop which you see as equals to V out, right. And that is what is V out is all about. So, now if you go on increasing the value of your M2 gate voltage and lowering your V in 1, then part of ISS will be transferred to M2, and therefore, you will automatically get. So, this will be less than ISS, this current, and this will be slightly greater than 0, and if you add the sum of them will always be equals to ISS, total current source. Now, that is the general scheme of things which you see. Now, you do have a capacitor here, which is basically a sort of a blocking capacitor, because it does not let any DC component to pass through it and reach to this particular point. It only lets the AC component to pass through it, because you do not want any DC component to load your subsequent stage. The subsequent stage now is basically your P3, right. We have finished with P2, this is P2 which we have done. So, this M3 was mirroring with M4, and this M3 was mirroring with M4, and the current was going through this point. As a result, it is going current through going the same current multiplied by RD is the voltage here, voltage appears across the PMOS here, right. Now, if you look very carefully, this is basically a pseudo NMOS inverter, and therefore, part 3 is basically a high swing stage. I will give you an example why. Say for example, this is, if you look very carefully, M6 and M7 forms an inverter pair, right, forms an inverter pair, which results in what? Which results in the fact that if you are using a VDD here, then approximately switching threshold will be approximately equals to VDD by 2. So, if the voltage here just crosses VDD by 2, this will ensure V out to go to latch to VDD, and when it is just below VDD, this will ensure this go to some other voltage. You see, you are feeding to the gate end of my device, right, feeding. So, when this voltage is 0, this is on, and therefore, this output voltage is latched to VDD, and the V out goes to 0. When this goes to 0, when this goes to 1 and this goes to, so let us suppose this is 0, then this is switched off, say this is 1, then this goes to 0, and therefore, this output goes to 0 when this M7 is 1, right. And as a result, you will have a large amount of current flowing through this particular point. You see, M6 has been made very large in dimensions, right. This is to ensure that your typical resistances are small and the voltage across these is very small, and you really get high end VDD full swing available to you in the output state. Who drives M7? It has been driven by this M8, look at the fact that this image is driving M7 and you have a current source here 30 microampere. This is also referred to as a band gap reference. We will not discuss at this particular point. Assume that band gap reference is basically current source which is basically temperature independent and is a very fixed current source which is given to a operational amplifier. The same current source is getting replicated at every other point. So, you see if this is 30, this is also 30 because you have a current mirroring action here. This is your CM current mirroring action here, and as a result you have 30 microampere here and approximately the same here provided, but you see here it is approximately 2.5 times or 3 2, so this is 4.5 and this is 14, right, and therefore what you will see is that you expect to see a large increase in the current here, and that is the reason you see this to be as equals to 90 microampere. The reason being this is approximately 3 times which you see, right. Now, so if you multiply for example 4.5 into 3, if you do, I get 5, this is 15, 13.5 which is approximately 14 micron, which means the 30 microampere will appear as 90 to 95 microampere at this particular point, and that is the reason you see a large amount of current flowing through here. This is the general structure of a CMOS operational amplifier. Let me come to the SPICE code of a CMOS operational amplifier. SPICE code is basically a code written in SPICE language. We will come to SPICE, we will have one module on SPICE later on, but at this stage the circuit in front of you gives you an idea about the basic idea about the sub circuit of the operational amplifier, and you can see here basically M1 is the M1, M2, M3, M4 are the entities which you are naming here, and these are basically the transistors which is being named here, and you have these are the nodes across which they are connected to each other. So, 4 2, 5 1 and so on and so forth. This is width, this is the length, this is the area of the drain, area of the source, then you have got perimeter of the drain and perimeter of the source. These are the 4 quantities, 5 quantities which are written for each one of them, and these are basically process dependent parameters which are inserted onto the system by the SPICE module developer. So, you do have certain sub circuits for all of them, and you have large number of for all the devices we first of all define its structure and how it looks like and across which 2 nodes they are connected. Then we define a dot model file which gives you an idea about the type of device it is. For example, VT0 is basically the threshold voltage of NMOS is been taken to be equals to 0.70 voltage, right. 0.7 volt is the threshold voltage of NMOS into consideration. We are also assuming that this is not an ideal current source, but a non-ideal current source with lambda equals to 0.04. So, this is 0.04 primarily meaning that the CLM parameter is basically 0.04, and therefore, when you plot a graph it will be something like this, slightly it will not be exactly the straight line across y axis. Similarly, gate to this is the capacitance of gate to bulk, gate to source, and this is gate to bulk, gate to source and gate to drain in picofarads, right. We have junction capacitances here, and we have got oxide capacitances, oxide thickness as 14 nanometer and so on and so forth. So, these are the model files for NMOS 1 and these are the model file for PMOS 1. So, PMOS 1 is exactly minus 0.7. So, they are perfectly symmetrical with respect to each other, but everything else almost remains the same, right. And this is how you write your SPICE code file for the CMOS operational amplifier. Now, when you want to find out the open loop gain, right, open loop gain basically so let me come back to this point. This basically if you look at this graph here, this is V out versus V in, which is basically also referred to as VTC. So, this is basically the VTC of an operational amplifier. So, you give an input swing from minus 0.2 to plus 0.2, right, and that is what is given here. So, if you see at V in, if you look at V in, then you see that I am giving VSS to be equals to 2.5, right, and connected between node 4 and 0 and DC bias, and VDD is 2.5 which I am giving here. V in is going from minus 2 volts, right, minus 2 volts to 0 volts, right, minus 2 to 0 volts, and I am able to get the picture here. Then I define load capacitance as 10 picofarad between node 3 and 0 and so on and so forth. So, what happens is that you just feed the circuit here and then you try to find out the value of your of the DC bias or the DC output bias at this particular point. Then what you get from this discussion is that you try to find out V out versus V in, which means that you give a sweep of V in. For every value of V in, you try to find out the V out, and as expected the VTC looks something like this, which is shown in front of you. So, when V in is very low, the output is 0, right, and it is very low. When V in is very high, one of the V in is very high, you get output to be very high, right. And this is, as we have already discussed this point in our earlier discussions of differential amplifier. But remember that when V in equals to 0, the difference between them should be equals to 0, then I should get output also should be equals to 0, but in reality not true. So, therefore, you always have an offset with you, and that is the reason I write here VOS. VOS basically the offset, which is this is basically your offset, voltage offset at corresponding to V in equals to 0, right. This offset does what? You have to add this offset later on into your system, subtract the offset later on. If it is a positive offset, you need to subtract it from the output, and if it is a negative offset, you need to add it to the output to get the achievable signal. So, you plot a phase, we plot a magnitude, which is basically gain versus frequency. So, this is your frequency spectrum which you do, right, and then you also plot phase versus frequency also using spice code. If you want to do it for unity gain configuration, unity gain basically means that you just short the input and output, right. So, you have a unity gain feedback loop, and therefore, that gives you a unity gain output. You get a VDD, as I discussed with you again, VDD, but here you use a dot AC because you are giving an AC cycle, and across a 10 mega ohm resistance you are trying to do it, and then you are trying to find out the transient value of the voltages at every particular point. So, when I find out V out versus V in, I see that this is basically your ID, which is basically on this side, and this one is on this side, right. So, I see that this is basically my ICMR, from this part to this part is my ICMR, input common mode range, right, and anything lower than this you force the device to be into the deep linear region, and if anything greater than this you allow it to be going to saturation region, right. And this is a spice code for the unity gain buffer which you see. Then we plot the same plot for PSRR and for your phase of PSRR. This is power supply rejection ratio. We will come to this later on, but very important part is that this power supply rejection ratio, this is basically the capability of the operational amplifier to remove noise from the power supply. And as you can see, at lower frequencies the gain is typically very high, it can remove very well, but as the frequency goes on increasing there is a drop in the output in this case. Similarly, for low frequency we get the same thing. We come to the last part, and that is basically transient analysis, and we see that for various different time analysis, timing analysis, how we get the output voltage with us. And the methodology adopted here is that again we do a transient analysis. So, rather than doing a DC analysis, we do a transient analysis. In the transient analysis, for a very short duration of time, we try to find out the output voltage changes because of the change in the input voltage, and we see that you will see that when my V in rises, my V out also rises, this diagram, but it rises with certain extra delay, which is expected also because that is basically the delay of the inverter itself. And but not only that, but one important point is that you see a small hump here and a small hump here. This hump is basically to do with the clock feed through, which means that because of very fast change in the output, there is a capacitive coupling between the output and the VDD, and as a result you will suddenly see a small hump in the output. Same thing happens in the lower transition when the output goes below a particular point, which is minus 0.1. So, even if your VDD is 0.1 to minus 0.1 for a very short duration of time, the output voltage can actually exceed 0.1 and go below minus 0.1, right, and that is because of the fact that you do have a capacitive coupling between the input and output, which results in a sort of a clock feed through mechanism in this case, right, and this results in a larger change. Let me therefore recapitulate to you and show you overall picture of the operational amplifier which we have designed till now. This example is, we have taken it from a standard operating manual, and we have found out that for a 2-stage op amp, your typical design we have taken out to be 5000. The same design principles, if we put it on a spice profile, we get approximately 10,000 as my simulation output. This is the gain bandwidth product of 5 megahertz, and we also get 5 megahertz here. ICMR is -1 to 2 volts, and it is plus 2.4 to -1.2 volts. So, it is almost the same thing. The slew rates are also equivalent. The power dissipation is typically very small. My output range is plus minus 2 volts for design. I was planning for plus 1 volt to minus 1 volt variation in the output, right. PSRR and phase noise margins and output resistances are also within the domain which is available to us. Now, the idea here was that to just give you a brief insight into SPICE, right, and how you can use the SPICE for multi-stage operational amplifier calculation. We will also come back to the SPICE module in details in maybe about 6 to 7 modules later on when we discuss SPICE. Then again I would recommend that you come back to this module once again, right, so that once you study the SPICE properly, you can come back to once again to this SPICE module for multi-stage amplifier, right. How to write a netlist, how to write a schematic entry in a SPICE, all will be told to you in subsequent modules. But at this stage I just showed to you that it is possible using simple SPICE tool to actually extract the values of gain, bandwidth, CMRR, slew rate, PSRR, open loop gain bandwidth product for a simple 2-stage operational amplifier. So, what we discussed here was basically your a 2-stage operational amplifier only. If you look very carefully here, what we discussed was basically a 2-stage operational amplifier, and as you can see here, this 2-stage operational amplifier was this 2-stage operational amplifier was working because of two main reasons, that you had part 2 which is basically primarily the differential amplifier part, which gives you a very high gain part, and you have got part 3 which helps you to give you a high swing part, right. So, you have an inverter which actually therefore pulls your output voltage directly to VDD up, or it goes down to VSS at a bottom low. So, this helps you to, so the part 3 part, which is basically this one, helps you to go for high swings, right, high swings, and this is high gain. This is your band gap reference which you see, BGR, right, and this is your VSS which you see as minus 2.5 volt supply which you give at this stage, right. And so what we did in this half an hour module was to give you an idea about the working principles of a 2-stage operational amplifier, where the first stage is differential and the second one is a high swing rate. We also saw the SPICE coding, how to do it, a methodology adopted. We will revert back to this module once again once we have finished SPICE module later on, and then we recapitulated by doing a comparison between the simulation results and the SPICE results, right, simulation SPICE results and handwork results together, and we saw they are very close to each other at certain point of time. I thank you for your patient hearing. Thanks once again.